Hello, everyone. So today we're going to again talk about shaft design, but this time we're going to solve some problems, right? So here is problem number one. We have 8 problems in total now. So in this case, we have a pure bending problem. It says here, find a suitable diameter for the following shaft. That is to be manufactured using EN5. EN5 is if you remember, the table that you have seen for the shaft materials yesterday. It has some standard specifications or designations. It's called EN something. So this is one of them. So this just tells you that you go to the table, find EN5 material or the designation for this material, and you based on that you can find the yield strength of the material, the elastic modulus, etc. Okay. If the acceptable limit, so the diameter is required at the beginning, then if the acceptable limit of deflection is 1.6 millimeter per meter of shaft, check the lateral direct deflection of the shaft. So this shaft cannot deflect more than 1.6 meter per 1 meter of the shaft. So we need to calculate also the maximum deflection or the maximum lateral deflection of the shaft. So we have 2 cases. The first case says that the shaft is restrained at the bearings. So you see here we have bearings, we have plain bearings. This is like axle for the train axle. Then you have the loads here, 25 kilonewton on each side. And then here is the shaft in the middle. This is the center line of the shaft. Okay. And here are kind of the wheels of the train. Okay. So first, if the shaft is restrained at the bearings and if the shaft pivots at the bearings. So we are going to solve these 2 cases. We are going to find the deflection for case 1 and 2. Also, you are required to comment on the answer. Why does the deflection in the ends of the shaft change when the shaft is allowed to pivot? And what type of bearing would allow this to happen? Okay, we're going to talk about this in detail. So the information that is given in the problem, first, the load is given, as you've seen, it's 25 kilonewton on each side. The total length of the shaft is 1190 millimeter. It's the, if I go back here, you see it's a 1 meter between the 2 bearings, and then you have 95 millimeter on each side. So the total length here is 1,190 millimeter. The length of the overhang, this part here between the bearing and the wheel is called the overhang. It is something like a cantilever. So if you have a shaft, for example, and then there is a bearing here, another bearing here, okay? So this portion here is called overhang, okay? Then here, the yield strength is 230 megapascal. This is, if you go to the learning pack, table 1, page number 9, I have just uploaded the learning packs as well on the Canvas page, but also you can find this in table number 1 from the PowerPoint slides. The Young's modulus of the material is given based on the table, 207 gigapascal. This is obviously steel. And the factor of safety for general applications is 2. So first, we are going to try to find the suitable shaft diameter using the von Mises failure criteria. Here is the equation that you have seen yesterday for the von Mises failure criteria. It says the equivalent von Mises stress value is equal to sigma 1 squared plus sigma 2 squared minus sigma 1 times sigma 2 to the power half is greater than S yield over the factor of safety. So sigma 1 and sigma 2 actually are the principal stresses. And in this case, if I go back here, based on what you see here, we have pure bending. So this is a pure bending problem. So you don't have any torsion, you don't have any axial forces. It's only pure bending. So in this case, sigma 1, which is the principal stress, is equal to sigma x only, because here obviously tau xy is equal to 0. You don't have any shear, so tau xy is equal to 0. And if you remember the sigma 1, this long equation, sigma 1 over 2 plus root sigma x over 2 squared plus tau xy squared. Okay, so and also for sigma 2, you have here a negative value. Okay, so in this case, sigma 2 is equal to 0, because it's going to be sigma x over 2 negative sigma x over 2. So sigma 2 here is equal to 0. So in the case of pure bending, you have sigma 1 is equal to sigma x. Sigma 2 is equal to 0, tau xy is equal to 0. So based on the von Mises theorem failure criteria, von Mises failure criteria, sigma 1 in this case is equal to sigma in the x direction, sigma 2 is equal to 0, tau xy is equal to 0. Consequently, in this equation, sigma 1 times sigma 2 is equal to 0. So if you substitute all these values into the von Mises failure criteria, so you will find that the equivalent stress is equal to the yield strength over the factor of safety. It is equal to sigma 1, where sigma 1 is sigma x. Then obviously here we have bending. If you remember, for bending, pure bending, the distribution of stresses is something like this. So you have maximum stresses at the outer fibers. You have 0. So if this is considered as x, and this is y. So in this case, sigma bending is sigma x. It is the sigma in the x direction. It is equal to sigma 1 eventually if you have pure bending. So in this case, sigma 1 is the sigma bending. And if you have pure bending, so sigma 1 is equal to sigma bending is equal to m times y over I. This is the bending stress equation, where m here is the bending moment, y and I depends on the geometry. In this case, we have a solid shaft, solid circular shaft. If this is the neutral axis of the shaft, so the distance between the neutral axis to the outer fiber here is y, where y here in this case is equal to the diameter divided by 2. So this is y value. Then the moment of area for a solid circular section is pi times the diameter to the power 4 over 64. So what we are going to do, we're going to substitute these two values into this equation here, which is derived from the von Mises failure criteria. So S yield over the factor of safety is equal to my over I. So m is the moment, bending moment, y and I are taken from here. So take these two equations, substitute in here to just eventually reach this equation here. So the diameter in this case is equal to 32 multiplied by the bending moment multiplied by the factor of safety divided by S yield times pi to the power 1/3. So what do we need here in order to find D? So we need the bending moment, we need the factor of safety, we need the yield strength of the material. So the factor of safety is 2. The yield strength of the material is given based on the material. And then only we need to calculate the bending moment, right? Okay, so in the first case, if we have a constrained shaft at the bearing, so the overhang portion that is from the bearing to the here, the center of the wheel, so we have 0.95, and this here shows you the constraint. If the shaft, you see here, the shaft is restrained at the bearing. So if the shaft is restrained at the bearing, so we're going to consider that the overhang portion is like a cantilever beam. So in this case, if you go back here, you see this portion here and this portion, even if you consider that you have a beam here, consider that you have a beam, something like this, and then here is these two wheels sitting on the track, and then you have forces here. You have 25 kilonewton here. You have 25 kilonewton here. Then, if you were to find the bending moment, let's say this is point A, this is point B, C, and D. So the bending moment at point C is equal to the bending moment at point D, and this is equal to the force 25 times 10 to the power 3 times the distance, which is 0.95. Even if you calculate the reaction forces due to the symmetry in the problem, so both the reaction forces are going to be the same, 25 kilonewton. Okay, so this here gives you the bending moment, the maximum bending moment, which is 25 times 10 to the power 3 times the distance. So we have the maximum bending moment. What we can do now, we can take this maximum bending moment, then substitute into this equation. Then, as I said, the factor of safety for general applications is 2. Let me just check here. You see here, it's the factor of safety for general applications is 2. Then the S yield, again, going back to the data here, you will see that the S yield is 230 megapascal. So 230 megapascal. Then you just substitute the data into here, and then it gives you the diameter is 59.47, right? But again, for manufacturing purposes, of course, you can just consider this as 60 mil. You cannot ask the guys in the workshop to manufacture a shaft for you with a diameter 59.47. This is going to be quite expensive, and it will take a lot of time, but just 60 could be like a standard dimension. So when the shaft is restrained at the bearings, okay, so we are going to treat the overhang portion as a cantilevered beam, okay? So this just means that you have here the force, the reaction force, 25 kilonewton. Then we have this distance here as the length of this cantilever beam, which is 0.95 meter. So you can use this equation that can be found in the deflection of beams table to calculate the maximum deflection in this case. So in the case of the shaft is restrained at the bearings, okay? So the maximum deflection is W, which is the force. In this case, it is 25 times 10 to the power 3. Then multiplied by the length, 0.95 cubed. And then here divided by 3, multiplied by the elastic modulus, multiplied by the moment of area. So the elastic modulus, if I go back here, you see the elastic modulus is 207 gigapascal. So the elastic modulus here is 207 gigapascal. But you just need to kind of work out the dimensions as well. If you're using everything in Newton meter, so this has to be in Pascal, so you just need to multiply by 10 to the power 9. And then I here for a solid circular shaft, it is pi over 4 times the diameter to the power 4 sorry, pi over 64 times the diameter to the power 4. Again, so just go back here. We've already found the diameter of the shaft. It is 60 mil, or if you want to be more accurate in the calculations, you can use the 59.47. And then this will give you the deflection, the maximum deflection in this case, right? So here for this equation, to be honest, I prefer to use Newton millimeter megapascal. This is how I do it. So you can just convert this 0.59. You can just substitute this as 95 mil. And then use the E value in megapascal. You just multiply by 10 to the power 3. In this case, it is Pascal now. And E, you just substitute the diameter as in millimeter. So this will give you millimeter to the power 4. But it's up to you. Eventually, it is 0.06 millimeter. If you go for the second case, where the shaft here, the shaft or the deflection, if the shaft pivots at each bearing. So there is one type of bearing. When we study bearings, you might just see this. It is called self-aligning bearing. The self-aligning bearings kind of rotates internally. The internal part of the bearing rotates with the deflection of the shaft. So it allows the shaft to deflect here at these points, okay? So in this case, if the shaft is restrained here, so it does not just kind of deflect here at this point. So if we draw how it deflects here, it will be something like this. So the deflection is maximum here at this end, okay? But the deflection here at this point is 0. And also the slope at this point is 0. So here, if the deflection is 0 and dy by dx is equal to 0 as well. But in this case here, no. So we have here kind of a deflection like this. So at these points, there is some sort of deflection. And the maximum deflection in this case is going to be in the middle. So here, delta static or delta is the Y max in the middle. So in this case, you have two forces, 25 kilonewton each on both sides. You have 25 kilonewton here. And then you have, let me just remove this so that you can see what I'm trying to talk about. So, and then you have the length, the total length. Remember, this length is equal to 1000 plus this 95 times 2 on each side. Then you have A, so A here is equal to 95 mil. Then if you substitute these values here into this equation, again, this equation can be found from the deflection of beams table. W here is the weight, which is 25 times 10 to the power 3 Newton, right? And then, as I said, the length is here. You just keep track of the units. Again, Newton, meter, megapascal is my favorite set of units. Sorry, Newton millimeter megapascal. So the force here is can be substituted in Newton, A in mil, then E is in megapascal, and then I in millimeter to the power 4. You can see the difference between the two deflections in this case. The deflection here, when we consider the restrained beam, is 0.06 millimeter, which is quite small. But here, if you were to install self-aligning bearings here at these 2 points, so the deflection of the shaft in the middle is going to be 6.56 millimeter, which is quite high. So let me move to problem number 2 then. So in problem number 2, we have another case. It's pure torsion this time. So pure bending, the first one, pure torsion, the second one. Okay. So it says the drive shaft of a permanent magnet generator is 1,000 millimeter in length. So we have here a 1 meter length shaft and transmits 15 kilowatt at 150 RPM. So the power transmitted is 15 kilowatt. The speed of the shaft is 150 RPM. So draw a suitable shaft arrangement. This is A. Then B, determine the shaft diameter. So the diameter of the shaft using EN8 carbon steel. So the material is given here. Diameter of the shaft is required. If the permissible torsion deflection is theta is equal to 3 degrees per meter of the shaft length, check the torsional deflection of the shaft. So 3 requirements: draw a suitable shaft arrangement, find the diameter, check the torsional deflection of the shaft. What is given here, the power is 15 kilowatt. The length of the shaft is 1,000 millimeter. The shaft speed is 150 RPM. The yield strength and the elastic modulus, they are coming from table number 1 based on EN8 carbon steel, these two. Okay. Then the shear modulus is the same. They are coming from the same table. So these 3, sorry. Okay. And then the factor of safety can be considered as to for general applications. So first, the suitable shaft arrangement. Actually, there are many possibilities here, but essentially you need to have a shaft with bearings and some sort of stepped shafts in order to locate actually the components. In fact, this is a shaft of a motor, not a generator, but I just thought to give you one example. And it seems like complicated, but what you need to focus on actually is this gray portion in the middle, which is the shaft. Okay, so this is the shaft of this motor. Okay, then you can even draw a view when you look from here. Then you see you have bearing here on the left hand side, on the right hand side, another bearing on the left hand side. And what is interesting as well is the snap rings. So if you zoom in here, you will find that this bearing here, the left hand side bearing, it has some sort of step. We have a step here. Then it has this particular part here is the snap ring. So this shoulder here prevents the bearing to move in this direction, and the snap ring prevents the bearing to move in this direction. So you just kind of sketch this somehow. It doesn't have to be perfect, but it's for you to understand that the shaft has to be stepped, and then there should be some sort of shoulders and other means to locate components actually. Okay. So next, we want to find the suitable shaft diameter. So the suitable shaft diameter based on pure torsion. Okay, so we have only tau xy here. So in this case, sigma 1, the maximum principal stress is equal to tau xy. And then sigma 2, the minimum principal stress is equal to tau xy. Sigma x is equal to 0 because you don't have any normal stresses. Sigma y is equal to 0. You have only torsion. And then sigma 1, sigma 2, they are both equal, and they equal to the shear stress due to torsion. In this case, if you apply the maximum shear stress theory or the distortion energy theory, you will find that eventually this tau xy value is equal to S yield in shear over the factor of safety in shear. In this case, if we use the maximum shear stress theory, you will find that tau xy eventually is equal to S yield over 2 times the factor of safety. So this S yield over 2, we consider this value as the S yield in shear. What we have here, we have the left-hand side because we have torsion. So if you have a cylinder or a shaft, and then this cylinder or this shaft is exposed to torsion, so the torque is T. And then if you look at the cross section here, you'll find that the radius is R, where the radius is just half of the diameter of the shaft. So then if you remember the distribution of the stresses for the torsion, it is something like this. You have maximum here, you have maximum here, and you have minimum in the middle. So this is how the tau xy is distributed. So the maximum stresses are at the edge or the outer fiber of this shaft. So that's why here, in order to have the maximum value of this, so R should be D over 2. That's why we take R is equal to D over 2. And then the polar second moment of area, J, is pi times the diameter of the shaft to the power 4 over 32. If you take Y and J, substitute them into this equation here at the top, so you will get this equation. So we have here tau xy is the torque multiplied by the radius over the polar moment of inertia is equal to S yield in shear over the factor of safety. Eventually, you take these two, substitute into here, you will get tau xy is equal to 16 times T over pi D to the power 3 is equal to S yield in shear over the factor of safety in shear. Okay. The next step is to try to find the torque. Let's go back to here. So the power is given and the speed of the shaft is given. So 15 kilowatt, 150 RPM. So omega is normally 2 pi over 2 pi n over 60. So n here is 150. So this is going to give you omega in radian per second. Then the power is 15, but remember, multiply by 10 to the power 3. This will give you Newton meter per second, which is watts. And then omega is in radian per second, so this gives you the torque in Newton meter. You can convert it to Newton mil, of course. And then use this equation from here, from this equation here. You can just simply rearrange the equation to have the diameter as 16 multiplied by the torque multiplied by the factor of safety over the S yield in shear. As I said, S yield in shear is just simply 0.5 multiplied by S yield. S yield is given based on the material. The factor of safety for general applications is considered as 2. Then the diameter can be calculated using this equation. Next, the third part in this problem, they are asking us to calculate the torsional shaft deflection. Remember, theta is TL over GJ. T is the torque, L is the length of the shaft, G and J. J is the polar moment of area, and G is the shear modulus of the shaft. If I go back here, you see it was given, the shear modulus of the shaft is given here as 82.7 gigapascal, okay? So you have already got the diameter of the shaft now, so you can just simply calculate J is like pi D to the power 4 over 32. Then the G is given. But one thing you can do here, you can calculate theta over L. which is T over GJ. Why? Because simply you consider here L as 1 meter, then this gives you 0.06 degrees per meter of the shaft. This way, if you go back here, it says the permissible value is 3 degrees per meter. So if you go here, you have got 0.06 degrees per meter. So we are far less than the permissible value, so we are okay. Problem number 3 says here, assembly supported steel shaft in the figure below is connected to an electric motor with a flexible coupling. So we have electric motor here, okay? Then we have a flexible coupling that connects the shaft of the motor to this shaft, okay? And find the value of the critical speed of rotation of the shaft. The shaft diameter is given as 5 millimeter. So this means that you calculate the shaft diameter based on the failure criteria or the deflection. And then based on that, you can calculate the critical shaft speed and compare it to the operating speed. So the length of the shaft is given here as 400 millimeter, and the diameter of the shaft is given as 5 millimeter. In this case, we are going to consider the case where we have a shaft under its own weight. So a simple supported and distributed load. If you consider that the maximum deflection here is going to happen in the middle point, so this is delta static, which is the maximum deflection at the middle point of the shaft. So the load per unit length is W. So this W is load per unit length. And then if the length of the shaft is L, so the values here for the reactions is W multiplied by L over 2. There is a symmetry here. So W, which is the load per unit length, multiplied by the length of the shaft, gives you the load, the total load in Newton, if this is in Newton per meter and this is in meter. So WL over 2 is the reaction on the left-hand side. WL over 2 is the reaction on the right-hand side. So, but how can we calculate the load per unit length? Because this is not given, okay? So by definition, it is the load per unit length. So what, do you remember the definition of the load per unit volume? It is called the specific weight. So specific weight gamma is the load per unit volume, all right? So if we, the load per unit volume, or it is the rho times G. So it is the density of the material multiplied by the gravitational acceleration. This is the definition of the specific weight. So if we multiply this weight per unit volume by the cross-sectional area, so it's the weight per unit volume times the cross-sectional area. This is going to give us the weight per unit length. So eventually what we can do, we can just simply take this value here, replace this value by rho G. So it is going to be is equal to rho G times the cross-sectional area is W over L. So the weight per unit length is eventually is equal to the density of the material multiplied by the gravitational acceleration multiplied by the cross-sectional area. If we consider that we have a circular, solid circular shaft here with diameter D, so it is the pi over 4 times D to the power 2. This is the cross-sectional area. Remember, if I go back here, the diameter of the shaft is given. So simply, we can now move on to calculate the value of W. So if we say here, we have a steel shaft, which is generally the case. So the density of the steel is 7830 kilogram per meter cubed. So what you can do now, this is the weight or the load per unit length. It is the cross-sectional area, pi, multiplied by the diameter of the shaft squared over 4, times the density times G. So this gives you the weight per unit length. What you need to do now, in order to calculate the critical speed of the shaft, we need to calculate the maximum deflection. So the maximum deflection, if you go back to the previous lecture, you will find that for this case, delta static is 5 multiplied by W multiplied by L to the power 4 divided by 384 EI. Remember that the diameter of the shaft is given as 5 millimeters. So you can just simply calculate the moment of area pi times the diameter to the power 4 over 64. And then the weight per unit length is being calculated, 1.51. Just watch the take care of the units, meter to the -1. And then the length of the shaft is given. If I go back here, so the length of the shaft is given as 400 mil. Okay, so L is given as 400 mil. And then the elastic modulus is 207 for steel times 10 to the power. It depends on how you are going to use this. 10 to the power 3, for example, this will give you megapascal. So again, you can just simply substitute everything in Newton, millimeter, megapascal, and then eventually you will get delta static in millimeter. Okay. Then here, the critical speed for this particular case where you have just a shaft under its own weight. This is the case number C in the table. The critical speed here is equal to √5 multiplied by G over 4 times delta static. Delta static is being calculated already. And then G is known, so substitute these values here to find the critical speed of the shaft. So problem number 4 here, we have seen like one problem where we had only bending, another problem we had torsion, but now we have combined loads or combined stresses. We have both bending and torsion at the same time. So we have the wash plant in a platinum mine is driven by the following equipment. So we have an equipment here. You see we have motor, and then we have on the right-hand side here, we have sprocket. Then we have a chain. Then we have another sprocket. Then we have a shaft. We have another sprocket, and this sprocket chain is extended, going down a well or something like that. So the chain is something like, if you have a bike, so you must have seen this, you have the sprocket, which is something similar to the gear, a toothed wheel. If this is the pitch circle diameter or the pitch circle of this sprocket, so it is something similar to the gear, actually, something like this. Okay, and then you have here between these you have some sort of pins, and around these pins you have, I hope that I'm doing it right, so you have something like this. Okay, and you have many of these like segments that is the chain. Okay, so it is something similar. So the thing is that for this combination, normally you have a small sprocket, and then you have larger sprocket. Okay, and then you have the chain going around them. Okay, so the idea here is that normally we have a tight side, then we have slack side or loose side. Okay, so if we assume that there is no pre-tension, so it's not pre-tight, so the force here, we have only one force on the tight side, so it is tension force on the tight side. So this is the force and the chain. Right. So this is the idea, guys, about the chain. So for the chain here, we have tension on one side, tension here, and these two forces are equal and opposite. And then again, for the sprocket in the middle here, we have tension here as well. Okay. So we need to consider these forces. For the intermediary shaft, so the intermediately shaft is this one here. Assume that both sprockets are key to the shaft. Okay, so this is the two sprockets that we are talking about. And that a suitable factor of safety is 2. So the factor of safety is given as 2. And then draw the bending moment diagram of this shaft, and then determine the suitable shaft size, which is the diameter in this case, if you have EN23 low alloy steel and using the maximum shear stress theory. Okay. So what I will do now, I'm gonna here first review what data we've got. You might not have seen this, but you see here we have the power is given 4 kilowatts. The RPM of the motor on the this sprocket are given is given as 90 RPM. The number of teeth on this sprocket is 19. The pitch circle diameter is 115.75. The pitch circle diameter of this sprocket is 230.168. The pitch circle diameter of this sprocket in the middle is 230.68, and the distances here are given. And these two sprockets, this one and this one, they have the same number of teeth, 38. So based on that, okay, so we have the power as 4 kilowatt or 4,000 watts. 90 RPM is the speed of the driving shaft or the motor. 19 teeth on this driving sprocket. Factor of safety is 2. The yield strength in shear is half of the yield strength of the yield strength of the material in tension. This is based on the table. And then this is our assumption here. And then the pitch center diameter of the intermediate sprocket is 230. This is given 230.68. Okay, and then I've shown you the pitch circle diameter and these bearing bends, etc. in here. This is the graph. Okay, right. So this is like a clearer picture of the intermediate shaft. You see here on the right-hand side, you have a sprocket where the sprocket, the pitch center diameter of the sprocket is 230.68. You have another sprocket in the middle here where the diameter is the same, 230.68. They both of the same size, same number of teeth, same diameter, and then the distances here are given 100, 130, 130. Okay? So as you see here, based on the configuration, so there is some sort of torque here on this shaft, intermediate shaft, and also bending. So we have combined bending and torsion. So first we can try to calculate the torque. So, but we calculate the torque for this particular shaft because the torque between this shaft and the motor shaft are different. The power is the same, but the torque is different. So the power, the torque is equal to the power divided by omega 2, where omega 2 here is the speed of this shaft, but we don't have the speed of this shaft. So, but we can exploit the idea of the gear ratio. We say that N1 over N2, which is the RPM of shaft 1. So RPM 1 of shaft 1, then RPM 2 for the second shaft is equal to the number of teeth on the sprocket number 2 divided by the number of teeth on sprocket number 1. Then we know the number of teeth on sprocket 1 and 2. It's 19 for 1, 38 for 2. We know the RPM for the first shaft, which is 90. So based on that, we can calculate the number of teeth for the shaft number 2. So, sorry, we can calculate the RPM for shaft number 2, which is 45 RPM. And again, omega is equal to 2 pi n over 60 to calculate the speed in radian per second. So the torque is equal to the power, which is 4,000 watts, divided by omega, and this gives us the torque. So this is how we calculate the torque in this case, based on the power and the omega, but the speed here, or the angular velocity of this shaft, had to be calculated the way that we did it. So next, we want to focus now on the bending, how we can find the maximum bending point or the maximum bending value on the shaft. So going back to the idea of the two sprockets, so we have small sprocket, we have large sprocket, and then we have a chain between them. And the tight side, the loose side, we have here FC. So here is the force is equal to 0 on the slack side. So FC here can be calculated using the idea of like FC is equal to the torque divided by the diameter over 2. So if we know the torque here or there, so if this rotates in this direction, this is going to rotate in this direction. And then we have torque 1 here, we have torque 2 here. So on this sprocket, we have already found the torque. If I go back here, so the torque here was found on this sprocket here, so which is, I called it 2. So in this case, the torque 2 over the diameter divided by 2, that gives you 2 multiplied by the torque over the pitch center diameter of this particular sprocket. If I go back here, remember the pitch center diameter of this, the pitch circle diameter of this sprocket is 230.68. So here we have the pitch center, the pitch circle diameter, and then we have here the torque. So this gives us the force on the tight side of the sprocket. If this is like the beam, we consider that this is our shaft here, or our beam, then at this point here, the force on the first sprocket, here we have a bearing at B, at A we have another bearing, and at C we have the second sprocket. So in this case, we have a force here, that is the force on the tight side, 7,359.38. Because these two sprockets, they have the same diameter, they have the same circle diameter, they have the same omega. So in this case, they transmit the same power, so they have the same torque, and consequently they have the same force on their tight side. So it means that the force here and the force here, they are the same. So what we need to do now, we need to calculate the maximum bending stresses on the shaft. We have reaction forces at bearing A and bearing B. Let me just go back here for a moment to just remind you by the graph. So in here, we have the force F on the chain. We have another force here, F on the chain. Then we have a bearing here. So we have a bearing here. So these are the two bearings, RB here, RA here. Okay. So what we have here, we have the same. We have the force here, FC, as I said, and then we have another force here, and then we have the reaction forces here. Okay. So using the equilibrium equations, we can calculate here both the reaction forces. I'm sure that it's quite simple for you now because you've studied mechanics 1, mechanics 2. So you get like summation the moments at point A is equal to 0. Then this will give you the reaction force P. Then you get summation the forces, apply this equation, summation of the forces in the y direction is equal to 0. If you consider all the forces going up, for example, positive. So this will give us the reaction forces at A and B. See here, the reaction force at B is negative, so it is opposite to what we have assumed. Okay. After we found both the reaction forces at A and B, so now it's quite simple to calculate the bending moment at each and every point. So A and D, the bending moment is 0 actually. So it is going to be at either C or B, right? If I go back here, so at this point here, okay, at this point here, and at this point here, these are the edges of this shaft, and you have point B here and point C here. Maybe you didn't see these designations probably. Okay, so going back here to this point here as 0 bending moment, this point here as 0 point bending moment. So in this case, we are going to calculate the bending moment at point P and C. Let me just get rid of this so that you see what is here. Okay, so the bending moment at point B is equal to this force multiplied by this distance. Okay, so it is simply it is the force, the chain force multiplied by 100. Okay, so this is the bending moment at point B. If I calculate the bending moment at point C, if I mean calculate from the same side, it is this force here multiplied by this distance. Okay, and because this force is going up, so it's going to be positive, and then this force multiplied by this distance, which is 130 here in this case. And the first distance, if you add 100 to 130, it's 230. But remember, the RP itself is negative, so you need to take this into account. So it is the first force multiplied by 230 plus the reaction multiplied by 130, but the reaction itself is negative. So when you consider this, so you will find the bending moment at point P and point C. And it is obvious here that the maximum bending moment is higher at point C. So the maximum bending moment is at point C. So for now, we calculated the torque. We have calculated also the moment. So we have bending moment, we have the torque. So you go there and then, okay, say the torque, the moment is maximum at point C. So we are going to use MC. Then the factor of safety is 2 for general applications. S yield is known based on the material. So you can calculate the diameter of the shaft, which is going to be, in this case, 43.58. So what you have seen now, if you have pure bending, you have pure torsion, or you have combined bending and torsion. Hopefully now you know how to approach this kind of problems and to find the suitable shaft diameter. And also we have seen one problem on critical speed, so you can understand. I hope that you understand now how to calculate the critical speed of shaft.